Okay, we're live. They're quietly reading. And the reason I wanted you to read, you should be done by now. If you're not, you Jim jacked around while I asked you to do this 10 minutes ago. But I like this because, puts together kind of what we discussed yesterday. An Euler circuit and then a Hamiltonian circuit. Why? Why are we doing this? Well, okay, you're not going to do this. But again, what I told you is the things that we're doing, we're just getting a real, I'm ADD. I'm getting a real, see now, hold on. Rudimentary, that's the word I was trying to think. It was a big word, that's why my brain locked up too, plus the distraction. A rudimentary, just a little highlighting of these general ideas. Then when I actually read, which would be you, when you're in college, if you had a silly class like this, reading the book actually puts everything in perspective. So I read for you, probably, someone that says you should be a Common Core teacher, you should make the students read and figure out their own destiny. It just takes longer. I actually just, yay! Okay, another distraction. Okay, so the driver of a street sweeper. What does the driver have to do? He has to sweep just a couple of the streets or all the streets? All the streets. So that's if we have a connection of different areas. Oh my word. If we have a connection of different areas and those connections are roads, the street sweeper needs to hit all those roads. Does the street sweeper want to sweep a road twice or just once? Just once. So he or she is interested in finding the best Euler path in order to make that happen. Put that hand down. It is, because I'm in the middle of a movie and I need to get this done before I answer any questions. Sometimes you need to take a deep breath. Now, what does a UPS driver want to do? UPS driver needs to what? Deliver. Does he need to go to a house twice? Yes or no? Like if there's two different roads to a house, does he have to take both roads to get to that house? No. Or various roads that just, okay, various roads to get that taken care of. Okay, so a delivery truck driver, which we're talking about, I just ordered something from Amazon. I always try to make it like something that I do. Just ordered something Monday morning, and I forgot to check my porch last night because I guaranteed that it would be delivered by Tuesday, probably in the evening. Well, that's because they don't do this by hand. I mean, come on. One UPS driver, I could imagine that they would have at least 40 deliveries they have to make in a day or more. That's just like a random thing. So that's 40 vertices, right? 40 different houses. So there's some sort of computer program that does what we're doing by hand for smaller scenarios, just to give you an idea. So a delivery truck driver wants to just visit the homes, just the vertices, once, not twice. Why would they go to the house twice? They just have to deliver one package. So that is why this pertains to a Hamiltonian path, right? I visit each vertex once and only once, and I want the best possible way that can happen. So, of course, for a UPS driver in the computer program, we got weights on the paths, and those weights are the distance traveled. And of course, for a UPS driver, the distance that you travel translates to more or less money and more or less time. Time is money for a business. So I found this a very powerful paragraph to actually synthesize like the last two ideas and why they are different, because they are very different as far as what they pertain to. So because I just wanted to redo this is actually the exact notes, maybe in a little clearer format from yesterday, and I'm going to build off of this and tell you some things that you have to do for your test on Friday. Anyone? Day. Just wish I could have been like that when I was in high school. Cool. All right, so again, I just choked on those words. The repetitive nearest neighbor. Cool. Okay? You actually have to go each vertex and find the lowest weighted Hamiltonian, very hard for me to say, circuit each starting vertex. But now, and then what I did is I have another question. I'm going to do the same thing, and I'm going to zoom in on this. And actually, this is a restatement of the notes, but then they're written real nicely. Like each one is drawn off to the side. So I'll post this, and then you can relook at this if it was a little fuzzy last night. I love how the homework worked, too. It was like a lot of asking about Euler circuits and then Hamiltonian paths and circuits and kind of comparing, kind of almost like a review in a way, trying to get both of them taken care of. So I don't want to redo all of this. I think first hour I did because I just felt first hour I needed to do a little bit better job, to be honest, just kind of explaining some stuff. But just to highlight a couple things, what I might ask you to do on Friday. What's Friday? All right. Okay, so we have to start from each vertex and find the best Hamiltonian weighted, lowest weighted circuit. So that's why we start at each of the different vertices. I'll just highlight the winner, and then what I might ask you to do. This would be given on the test, and I'm going to ask you to sketch the best one, and all the rest we could just write numbers. On the next example, when I do a Hamiltonian circuit, I'm just going to write the numbers. And then maybe, emulate what you'd have to do by drawing the winner. But I think I think we did something wrong first hour, because I didn't think there was 4 ties. So please help me on the math. It was a little fuzzy in the morning. So I'm going to do the second one only. So you start with A. Again, it's kind of tough. I cheat because I have this program that I'm able to use the highlighter and erase it and then reuse this drawing. All right, so 12, 11, 12, or 19, which one's the best? 11, that's the shortest path from A to start off. Okay, then, so that's why we have an 11 here, from A to D, and it's denoted A to D. Okay, then, what's the next one that I can use? 6, 7, or 18, what's the best? 6, that's why we see 6, and that's a connection from D to E. I'm only going to do this one because I think you should get the idea. The idea of a Hamiltonian, least repetitive or whatever. Well, I probably forget the names. I'm getting myself jumbled up already. Repetitive nearest neighbor is getting the lowest number from each vertex and then checking which one's the best. 5 vertices, 5 checks, 5 pieces of work. Okay, so that's what we're doing here. Now, can I do 12? Yes or no? Can I do this? No, because that closes the circuit already. What would happen with that is I would end up with something that's bad, and then I have to keep going. I don't have C and D connected, and I would visit A more than once, which is not good. So my only choices are 14 or 16. What's better? 14. So now I'm stuck. This may or may not be the best thing. I'll tell you some things that are in the book about this as well. These 5 may not be the best scenario overall still, especially when the vertices explode and get a lot more. So that's why computer programs are really what UPS uses. But the programmers know all this stuff. That's where you make the money. The people that have these ideas can able to program the situation so if this driver has 40 vertices with all the distances listed in there, it will get the minimum, weighted graph, meaning the minimum amount of time they have to travel in order to get this done. Anyone ever see a UPS driver or a FedEx driver? Mostly UPS drivers, when they get out of that truck, what do? A lot of times they run because they're on the clock. I bet you they're monitored. You're like Big Brother. But also I think it's incentive. I've seen UPS drivers run to deliver a package or walk briskly in and out. I'm sure there's some sort of incentive program because of that. But anyway, I'm going to mention them quite a bit. Now, the next thing, I can't go to 19. I can't go to 18 back to D. I have to go to 13. That connects C. And I started with A, so I have to end at A. All right? And then what you might have to do is actually draw that subgraph then. Okay, so do the math, get the best one, and then, hey, maybe off to the side, whatever the best one is, draw the route, all right? And then make sure you can do that. Okay, so, watching the next one, hopefully it won't be that bad. Okay, so here's what I'm going to do adding to this. All right, I know you're going to laugh at me because I'm a, silly little, person. But this is realistic. A lot of times our plans for the day are just we gotta do some shopping. Well, we gotta have lunch because it's fun. Might go see a movie, at the mall, and might have to shop at different places. So we start at where? Where do we start? Pointing right at it. Home. Then I'm going to go to lunch. Of course, then we'll play that game that I told you. We'll put all the, you remember that one, right? We vote on what we're going to have for lunch by, never mind, a weighted democracy system that we learned about in Chapter 4. And then the mall for a movie, and then let's say Kohl's, and then Walmart. What's the shortest distance to cover all of those things? That would be what we could do with a Hamiltonian circuit. So from this chart, I'm going to expect you to make a drawing, a map. So I could give you a chart on the quiz or test, and then I have one that's assigned that has a chart. And from this, find the 5, how many vertices are there? I have it up there. How many vertices? How many different places? I already said it. 5. From that, find the best path using the repetitive nearest neighbor situation. So this may or may not be what I have up here. I'm going to use what the book has because it helps me for highlighting. But here's what you do. I got my cord in the way. You make a graph out of this. I'm going to lose like 5 pounds today. I think gas station I'll use GA, and then grocery store I'll use GR. I'll use a capital R because that really kind of sticks out better than my lowercase r. And again, we can make this exactly like what we had on our notes from yesterday, a pentagram, kind of situation. What do we have? Video store maybe. This may not emulate what the book has, but it'll be close enough. Shoe store, which could be S, and then we could just make H home. Now what we can do, I do have to zoom back a little bit in making this. Okay, of course the video store doesn't go to the video store. Video store to the gas station is GA2. Right? And then the video station to the grocery store is... Now this is going to be a little jacked up compared to what we have over here, but make sure you just understand how to create this graph, and you don't have to copy mine. But what you're going to have to do is, for the notes, use my drawing that I have from the book and understand it. Ooh, rumble, rumble. Okay? Got some thunderstorms going on here. Video store to the shoe store is a 10. Make sure I don't make any mistakes. Then the video store to home, we got to make that an 8. Oh, I almost missed. Really keep those tight. You might have to erase if you draw another line and the numbers. I'm not sure which number's on which line. Your job. You got to figure that out. I'm going to cheat. Cheat because you don't have this option, or maybe you have more colored pencils with you. Now I got all these down. I'm going to go red for this. Now, someone brought up a great point. I hit red 3 times. I don't have to worry about those because these will all be covered. These are back and forth between the various places. So, gas station to the grocery store. That's easy. And that's a 1. Shoe store, which is over here. I'm going to put a real tight 11 on that. And then home, I'm going to put an 8.5. Try to keep the colors tight with those numbers so then they really pop and stick out. Then I'll go purple. And again, sorry if you're colorblind. Grocery store to the shoe store. I have had that happen. And then these notes don't look as, got yelled at consistently for it. And then the last color, maybe orange. No, blue. No, or black. Okay. And then there's only one thing left to 6 that goes from, that's easy, shoe store to home. Yeah, I don't know if black really sticks out. Okay, so you got all these numbers on this, and then what you have to do for a Hamiltonian circuit is check each vertex. There are 5 checks for this. I'm not going to list the vertices. I'm just going to do the numbers now. because that will be easy. All right. So there we go. I cheated. I used the books thing. Okay. So here we go. Just going to flow with the movie. You can watch or not. It's your grade. All right. First thing we're going to start with is from the gas store. Now, again, was this exactly right? I think I did have gas and grocery. Did I have shoe store down here in this corner? No, I didn't. I had it switched, right? I had home and shoe switched. Not a big deal. Okay, this is the graph I'm using. Okay, I just wanted, because it works better for how I'm marking this. I'm going to start with the gas station. So check 1 is starting from the gas station. Now you're going to find out this doesn't mean I live at the gas station. Where do I live? I live at home. So we're going to start this trip where? Where are we going to start the trip? Starts with an H. Home. So why am I starting at the gas station? Just watch. Watch when I'm done with this, how this works. I'm going to start from the gas station. What's the best edge to choose first? Choose. The one that is a number what? We already missed it. There's a number smaller than 2. 1. So I'm just going to, okay, gas to grocery. So that's a 1. I'm just going to put the numbers. Okay, now we're at the grocery store. So again, this is how this works. We have to go from the grocery store now to who? 5, 7, or 9? What's smaller? 5. So put a 5 there. These weights are miles. Less distance is better. Okay, now where do I go from here? That would close the circuit. Yeah, I can't do that. And then if I continued, then I'd visit the gas station twice. And I only want to go there once. So that's part of the rules of a repetitive nearest neighbor. You don't close the circuit until you go back to where you started. So 8 or 10? 8. Then 6. Then where do we have to end up? Gas, which is a what number? 11. Make sure that we don't miss those numbers. Okay, that's 31. All right, now, before I move on to the next one, does this mean I live at the gas station, I start from the gas station and end up at the gas station when I'm done? No. Look, couldn't I still take this path, start at home, and do one of 2 things? Go this way to the video store, then to the grocery store, then to the gas station, then to the shoe store, and then home. Yes or no? Yes. So the point of starting at a different vertex to check the Hamiltonian circuit and have to do it at all 5 vertices is to find the best one, but then also we still can start every one of these at home, even though we're looking at a different vertex to find this weighted system. So I hope you understand that, and I know we didn't yesterday because I didn't explain it very well in those terms because we didn't have a real world situation tied to it. Whatever. Okay, so this is gas that I started with. Now let's start with grocery. So grocery is the second check. And then we can go faster. Okay, starting at grocery, what do I get to do? Gas. Then what? Video. Then what? I can't do 5, because then I'm at the grocery store again. So it's home, right? Then what? It has to be shoe, and then what? Grocery. So I can write those numbers. 1 plus 2 plus 8 plus 6 plus 9. And then we'll add that offline, making sure we don't make a mistake. Okay, so we got 26 on that one. So far, that wins. Oh, and by the way, back. Does this mean I live at the grocery store and end up at the grocery store? No, I could start at home, and I have 2 ways I could do this. I could either go this way, whoops, and then this is how I travel, or I could go this way, and this is how I travel. Maybe I want to go to the shoe store first, all right? But you got to make a choice. It's either shoe store or video first. Depending on how you do it. If there was food in here, I'm hungry now. Kids are screaming in the back. I better get to lunch first before we go to a movie or something like that. Otherwise, I'll have anarchy in my hands. Shoe. So this is expectations of what you need to write as a student. Starting from the shoe store, where do I go? Home. Where do I go? 8, 8.5, 7. 7. Where do I go next? Gas, 1. Where do I go next? Video, 2. Where do I go next? Back to the shoe store, which is a tenner. So this is a different little situation. So I started at the shoe store. I went 6. Then I went 7. Then I went 1. Then I went 2. Then I went 10. Add that up. Zoom out. Does that zoom out? Get smaller. Then we start from home. Well, that's where we should be starting. Remember, all of these I could go back to home and still complete the circuit. Home to home. Just a way of testing this. Where do we go first? Shoe. Then what? 9 or 11 or 10? 9. Then what? 1. Then what? Oh, I went through the gas station and crashed. Then what? 2. And then we got the bums falling asleep. Where do we go? Back to home. So guess what this is exactly the same thing as? This is the same as this one. So this one is also a 26. So again, this is kind of a bad example because not uniqueness. There's not uniqueness in the numbers. Of course, in a test, we'll have all 5 tests, and I will probably have 1 or maybe a tie. So you have options of the way to do this. But, you know, that's what you got to be aware of and be ready for. So I just put 26 because I knew I ended up with the same path as that one before. All right, sorry, meant the eraser there. Last one, I did not check starting from the video store, which will probably get something very similar here. But where do we start for the video store? 2, 5, 10, or 8. 2, then what? 1, then what? It's either 7 or 9. 7. Now, what do I have to do? I have no choice because I can't go to a vertex that's already there. 6, and then what? 10. And if you guys realize, number 5's drawing is exactly as number 3's drawing. When we did 3's drawing, it ended up being the same path, just started in a different direction. So again, just emulating what happens. Nothing really special happened in this particular example, trying to find the Hamiltonian circuit using the nearest neighbor algorithm. So now what we're going to do is our new notes. So this is actually our notes for the day, our new concept. It's up to you to get this down and understand what's going on. In the previous example, nearest neighbor, you started from one vertex to another, then you had to keep going. From that vertex to the next one, then from that one to the next one, and that one to the next one until you completed the circuit under the rules. Cheapest link, there's one good thing. There's only one check. There's not 5 checks. So that's one good thing. And by the way, as you're writing this down, I did say this before, even that last algorithm, they use the term approximately. What's the best situation? Wow, is that loud? Because even the algorithm's not perfect. The more the vertices, you're going to need a computer program to actually put a whole bunch of concepts together to get the best path. Again, talking about the UPS driver with 40 homes he's got to visit in a day. I don't even know if that's right. Maybe quite a bit more. It all depends. So the cheapest link, this is kind of weird, and I pulled something out of the book that's a little bit repetitive, but it just when I read it, it just solidified it for me further. You're not so restricted to what you have to do, and that's why there's only one cheapest link algorithm to do with a drawing. And again, it may or may not be the best. That's why they say approximate. So based on a need for each vertex in the Hamiltonian circuit to have degree 2. Now, this is what solidifies this. Why degree 2? I'm a UPS driver. If it's degree 3, then I visited that house how many times? Think about it. So if at degree 2, here's a house, and there's an edge, and there's an edge. What does that mean I did at that house? I arrived, and then what? I left. If there's another vertex, and that's degree 3, what does that mean I did? I arrived, I left, and then what? I came back. Why would I come back to the house again? So that explains why this is the case. In a cheapest link scenario, we want to make sure we avoid getting a degree 3 or higher, it should say vertex. Okay, it actually does say a third edge at any vertex, because it doesn't make sense for what we're trying to do. So I hope that is clear. And it really should be. Because the whole idea of what a Hamiltonian circuit is supposed to be doing, just think Hamiltonian circuit equals UPS driver. And then as you're writing this down, Euler circuit represents who? Street sweeper, where the street sweeper has to hit every street, but how many times? Once. Why would you sweep the street twice? Try to say that 5 times quick. Not right now on your own time. So back to this. I think all the words I'm using right now, if you're just listening, this will make this a lot easier. Okay, so at the start, all edges are acceptable. So you have to select an edge. You have to connect something. The UPS driver has to go from this connection to this one. So the first one you're going to pick is the one with the lowest weight, because that's the shortest distance between two of the houses that he has to go to. Certainly one that we want to do. I tried to warn you. I tried to warn you. Next one is do it again. Try to find the next edge that is the smallest weight without doing the orange things. Now you're not stuck with connecting. All you have to do is look around and find the smallest edge, then find another smallest edge. They don't have to be connected. But what you can't do is create a vertex that gets degree 3 or higher, and you can't close the circuit until you end up where you started. So you only close the circuit when all the edges have played. I'm sorry, all the vertices are connected in some way, shape, or form. Then you close the circuit at the end. But you can't do it early, just like in repetitive nearest neighbor situation. Okay, so always with words, it's not always the best thing to see when we first get it. I gave you time to look at that. So again, the cheapest link algorithm directs you to create a Hamiltonian circuit by always picking the lowest cost edge that does not add a third degree. I am not going to a house twice. I'm going to a house once. That's what this guarantees, UPS driver. In other words, we must avoid creating a graph in which any vertex has degree 3 or higher. In addition, we must also avoid choosing an edge that would complete a circuit before we have a full Hamiltonian circuit. That is the same thing in our last thing that we had to do. Okay, we can't do that. So those are the two restrictions in doing the cheapest link algorithm. So here's a little drawing. I'll move back. I'll use the glory and power of the highlighter, and then we'll write the final answer as a subgraph. Remember, this is a graph, and then a subgraph is a copy from this. So I actually could have had this drawn just like a pentagram, because how many vertices do you see? How many houses do we have to visit? Count them. How many vertices are there? 5. This is just a different representation of the same thing. Okay? So give you a second to write that down. And do remember, I almost hit stop. Whew, that was close to a big mistake there. Remember that we don't have intersections here. This is just another representation due to a graph. These don't intersect here. That's not a vertex. I think that's the only place where we don't have them. But E is, right? And there's no rhyme or reason. This person just decided to draw this way instead of a pentagram. All right? It is a connected graph. All the vertices are connected with other vertices. Okay? Shh. All right, here we go. What's the best edge? I love that little downtime on YouTube. Are you going to say something? What's the best one I should choose? What's the best one? Choose. What number is the smallest? AE. So, here's what I mean about the cheapest link algorithm. I definitely want to go from A to E or E to A at some point in this trip. And by the way, I'm a UPS driver. Let's use B as the base. So where do I have to start when I do my trip? Say it. B. But it doesn't matter. You know, when I'm done with this, we can just go ahead and take our answer, and then we have we'll show you. All right, so this will take care of it. All right, what's the next one? That's the next smallest situation. CD. Can I select those? Yes or no? Okay. I only have degree 1 here and degree 1 and degree 1 and degree 1. This is what I mean about no more than degree 2 on each vertex. We're making a subgraph out of this. I'm fine right now, and I did not have to go in order. What I'm doing is trying to select all the smallest edges without creating a degree 3 and without closing the circuit too early. Okay, so now what? What's the next one I choose? So what's the next smallest number? B to A, which is 13. Can I choose it? Yes or no? Yeah, because what's the degree of A right now? Wait, there's something smaller? Yeah, I did that first hour. I could never count. 11, 13, 12. Wrong! That's what my first grade teacher said. Right? So I got to select 12. 12 is smaller. Okay? All right, now what can I choose? Can I choose 13 now, yes or no? No. Here's why, UPS driver. At some point, the UPS driver is going to go to A, it's going to leave A, and then somehow end up back at A. Why would I go to that house twice? Why would I? I wouldn't. So I do not choose that one. That's against the rules. Who's the next one I can choose? Okay, well, who hasn't been involved yet? What vertices? B or? Oh, just B. You're right. Sorry. My bad, dog's roof. Okay, so what do I have to choose? What do you think? B what? BE, because the only other choice would have been B to D, which we eventually have to do anyway, because we have to get this back to a connection here. And this only has, what's the degree of this vertex right now? What's the degree of this vertex? 1. What's the degree of this vertex? 1. All the rest of them are degree what? 2. So I couldn't avoid using this one. So I had to use that 28 at the end. Now again, could this possibly be the best possible situation? Maybe, maybe not. Jumping back, rewriting this as a subgraph to get what the route would be, this might be what you have to do. Okay? All right, what's the subgraph? What actually happens with this Hamiltonian circuit? And then this UPS driver would drive 78 miles if they did it this way. Now, like I said, where did we start? We started connecting A and E. But now when you look at the final answer, base is here. So this person has two choices. It could start this way or start this way. Either one, right? So that's the choice that this person has using the cheapest link situation. All right, and then you go ahead and add those edges up, and there's only one answer. As far as how this all goes about. So, okay, all right. So it'd be good to know where does it actually start, but it doesn't matter. You still do the cheapest link algorithm, and then at the end, okay, fine. I could go from B to D, then D to C, C all the way to A to E, and then E back to B, or I could reverse it. So this might be different down here, what they say according to what I decided to call this. Okay, I'll leave that up there for a second. Boom! We already did this one, right? We already had this graph, right? Okay, now all I'm going to do is the cheapest link algorithm with this. And then I bet you it will be it'll be one of one of the answers that we had with the nearest neighbor algorithm. So cheapest link, just to understand the order of things. Who do I choose first? What one for sure? What number? 1. Oh, I thought you were sleeping. I was about to destroy the cabinet again. These kids. All right, what's the next one? 2. Why is he failing? All right, what's next? 6. See, I don't have to connect them. Okay, these are valid choices. Okay, so now who's next? Ooh, this gets crazy now. Can I do this one because it's 5? No, because that completes a circuit. And I don't want to complete the circuit yet. And then, and besides, the next step, if I did complete that circuit, I'd have a 3 edge, or degree 3. So what do I have to choose? I have 7 I could choose. I have 9 I could choose. I have 8 I could choose. Which one's best? 7, because that's the smallest number that's left over to keep no more than degree 2 for the edges. Now I'm stuck with who? 10. But what you have to understand is this is the only answer for the cheapest link algorithm by following the order and picking valid edges. There is no more. than that. Now, it's only 5 vertices. This doesn't mean that if I do the cheapest link algorithm and the nearest neighbor algorithm, one of them is going to copy. The more vertices, the more complicated. We're doing Mickey Mouse examples that we can do by hand. So again, this one ended up being 26, which is one of the answers that we had the other way. Just wanted to emulate the cheapest link algorithm with that question because that's what you have to do in your homework, actually.